Welcome back everyone. In the last lecture we had seen how to design state feedback controllers, and we saw that the control law u equal to minus kx plus nr helps us to reach a steady state value of the output and also helps us to stabilize the system. The K matrix or the controller gain matrix helps you to stabilize the system, because the eigenvalues of A minus Bk you can place arbitrarily wherever you want to if the system is controllable, and the NR part or the feed forward control part helps you to reach the steady state value that you desire at the output. And we also ended the last lecture with this crucial question as to, if I have to implement u equal to minus kx plus nr, how do I get the information about the states? And this is what brings us to observability and observers. The idea is that we would use the informations available to us about the system to somehow create or estimate the states of the system. And if we can successfully estimate the state of the actual system or actual plant, we can use those estimated states to feedback the state variables into the controller, like u equal to minus kx, where x will be coming from these estimators. How do we design these estimators? Is it possible to design such estimators? These are the questions that we are going to answer today. So, we know that if we are given a plant, we can model the plant as x dot equal to ax plus bu, and the solution of this state equation is given by xt equal to e to the power of at x naught plus this integration term. Now, notice that this system is the physical system that you have. Now, in this case, since I have already modeled the system, I know the value of A and B, or the matrix state matrix A and B. Further, I will also know what input I am giving to the system. So, one can assume that what if I use the A, B and U information to create a digital copy of this system, or even a physical copy of the system. Because I know A, B, I can create another system which is the same state matrix and input matrix, and if I know that, I just give input u to the system and I run the system, and if I run the system, I can get the values of x. However, there is a catch there. The catch is that you can look at the expression for state trajectories, you can see that the initial condition plays a role as to what will be the state trajectories of the system. But for a plant, I might not know what the initial conditions of the system are, because I have started the system and it is working on its own. The other problem can be that, suppose physically the system is running, you started the system yesterday itself, say, and you do not know when the system exact time, you do not know the exact time when the system has started. In that case, today if you create a copy of this system and start the system, the states that you will get will not be exactly similar to the states that the actual system is having. So, these are certain issues that you might face. So, what I am claiming is that, say I create this digital copy or another physical system using the A, B matrices and the input that is known to me, and I say that let the initial conditions of the system be 0. In that case, for this copy that you have created, the state trajectories will evolve according to this equation, because the initial conditions I have chosen to be 0. Remember, this is not the actual system, this is not the actual system. This is the system that you have created, you have copied the system, you have created a version of the system and you are running this system to get what is known as x hat t. X hat t is the estimated state, this is not the actual state. So, when I run this system with an initial condition of 0, these are the estimated states that you will get. Now, notice that if I subtract x t and x hat t, I will get e to the power of a t x naught, because of the expressions that you have, you can directly see that you will get e to the power of a t x naught. Now, if we assume that the system initially to start off with was a stable system, that means the eigenvalues of the matrix A are always on the left half of the complex plane, then you notice that if you do limit of t tending to infinity of E of t, you will get limit of t tending to infinity e to the power of a t x naught. Again, A can be written as t j t inverse, where j is either Jordan canonical form or diagonal form. We can always do this, we have already seen this earlier. I can always find out a T matrix like that, and once I do that, I can take this T out. We can write it down as T to the power of j t T inverse x naught. Since T and T inverse and x naught does not depend on time, I can take the limit inside, and finally I will get limit of t tending to infinity e to the power of j t. Now, what is e to the power of j t? Suppose e to the power of j t was something like this, you know that e to the power of j t will come out to be something like this. Then, if the J matrix was a Jordan matrix, then e to the power of j t might come out something like this. This is just an example. So, if this is the case, if we get a matrix of this form, notice that this lambda 1, lambda 2, lambda 1 and lambda 2 are eigenvalues of the A matrix, and they are on the left half of the complex plane, which means limit t tending to infinity, this matrix will go to 0, and which in other word means that limit t tending to infinity, the error signal will become equal to 0. And what is the meaning of the error signal getting 0? Error signal becoming equal to 0 is nothing but limit of x t minus x hat t at t tending to infinity becoming 0, which means at t tending to infinity, the actual state and the estimated states are the same. Let us look at a simulation to understand this effect. Here I have taken a system A equal to minus 0.510 minus 1. This is the system that I have taken. B is 0 1. I will talk about this later. Say for example, the input given is 1. Now, this is the actual system. I am integrating this one. So, I am simulating this system x dot equal to ax plus bu. Okay. Forget about this part now, I will come to this. So, I am simulating x dot equal to ax plus bu. This is the actual system, the actual plant, and I have also created a estimator by the algorithm that I have just now shown, that I am simulating ax hat plus bu, where the initial conditions I am assuming to be 0. The actual system has suppose initial condition 1 minus 1. This is not known to me. Okay. So, this system is running on its own physically, initial conditions were 1 and minus 1, which is not known to me. It has been running for a long time and the initial conditions were 1 and minus 1. I created a digital copy of that system or a physical copy of that system using AB matrices. U I know, U is 1 here, and using that I have just assumed that the initial condition is 0 0. So, wrong initial guess. I have taken a wrong initial guess, and now I will simulate both this system together and see how the output would be. Notice my A matrix is this. If you can check, let me just check the eigenvalues of A matrix. If you look at the eigenvalues of the A matrix, this is my A matrix. So, the eigenvalues of A matrix will be minus 0.5 and minus 1. So, this is a stable system. Okay. So, let us see what happens. So, here the black line here is the physical plant, the actual plant. So, the states are evolving like in the given in the black line, and the dotted lines, red line is the estimated state. So, we have estimated the state, and notice that at t tending to infinity, remember when we say t tending to infinity, theoretically it means t tending to infinity, but practically it means that you run the system for a long time, and after a long time you can see that the system, the estimated states and the physical states do align with each other. So, basically I have successfully estimated the states of the system, and these are the estimated states which I can maybe use for the state feedback controller. I will come to that soon. However, there is a problem with this. Now, what is the problem? Now, think about it. Suppose you have the system. Okay, the system is running physically somewhere, you created this copy and you are running it, suppose on a processor or somewhere you are running it and you are taking the states. Now, for some reason, say the actual plant got some disturbance, okay, it got subjected to some disturbance, and as a result of that the states will gets disturbed, right. It will no longer follow the differential equation x dot equal to ax plus bu, but maybe something like x dot equal to ax plus bu plus some noise. Now, the copy that you had created, the physical copy or the estimator that you have created does not know about that disturbance, right, because it does not have any feedback from the actual system. Okay. Then what will happen? Let us look at that. So, here comes this part. So, I am taking a disturbance of 0.2 and say I am adding it to the actual system. So, the actual system has a disturbance now that is getting added. Okay. The estimator does not know about this disturbance. Let us have a look at what happens. Notice that the estimator is no longer able to track the actual states. There is a difference, right. And this is the problem with this type of an estimator. This estimator is known as an open loop estimator because it does not have any information about the actual physical plant. Okay. So, it is not taking any feedback from the actual physical plant, and that is the reason this type of an estimator will not work. As a matter of fact, you can even go ahead and check that if your A matrix is not stable, or in other words, if A matrix has eigenvalues which are on the right half, at least even one eigenvalue is in the right half, you will not be able to track the states. Okay. So, this is the problem with this type of an estimator. By the way, in the simulation, if you look at the simulation, you see I have only plotted the first state. Okay. I am only plotting the first state, I have not plotted the entire states. Okay. I am only plotting the first state. See, remember this is a second order system, we have two states, I am just checking the first state. You can also go ahead and plot the second state also, you will get similar results. Okay. I am just showing you that the first state itself is not getting tracked, then how come it will track the second state. Okay. You can go ahead and do the same simulation for the second state as well. Now, coming back to what we were discussing, that you see we have some issue here. So, this open loop estimator is not going to work because we do not have any feedback from the actual system. Okay. Now, we ask another question then. Fine, we do not have the open loop estimator cannot be used. Can I use the output and the input information of the system, actual system, to get to the states? And why am I asking that question? For example, hypothetically, suppose you have 100 states in a system and you want to, if you want to implement u equal to minus kx plus nr, this state feedback law, you will need all the 100 states. Now, it is not physically possible for you to put sensors to measure each of these states. Okay. You will need 100 number of sensors then, which is not physically possible. However, I can measure the output, because output is y equal to cx plus du. Output, there are only p number of outputs. I can check or I can measure the outputs. Now, using the output information and the input information is again available to us. Will I be able to reconstruct or estimate the states of the system? This is the question that we will ask now. See, remember, in the open loop case, in the open loop estimator, I have not even used the output information. I just created a copy, right? So now we saw that there is a problem. So now we are thinking, why not use the output information? Because the output information of the plant is available to us. Maybe it can help us in getting to the states of the system. Okay, and this brings us to the concept of observability. So, what is observability? A system is said to be observable for any initial condition xt naught if by using the output and the input information you can find out the state of the system within a finite interval of time. So, if you have information about the input and the output of the system for a finite interval of time, you have taken measurements of the input and output for a finite interval of time, using that information you can easily find out the states of the system. If you can do that, for irrespective of whatever initial condition the system has started with, we say that the system is observable. Now, this is a strong statement, because what I am saying is that if a system is observable, what can I do? If a system is observable, this means you measure the input for a finite interval of time, you measure the output for a finite interval of time, and then using these two informations, you can go ahead and recreate the states of the system or estimate the states of the system, irrespective of whatever initial condition the system started with, because the initial condition idea we do not have. How at what initial condition did the system started, we do not have that information. So, this is a very strong statement. So, if a system is observable, we will be able to do that. Okay, but question is, how will we be able to do that, and why is this even true? Okay, let us look at that. So, for example, suppose you have this system x dot equal to x plus bu and y equal to cx plus du. We know that the state trajectories will be given by this. Now, the question we are asking is, can we use the output to get the states? Now, you see, I can go ahead and write down this equation that we have here, y equal to cx plus du. This equation can be written as cx equal to y minus du. Now, a valid question to ask would be, if I can rewrite this equation in this form, then why not I just solve this equation. Remember, this is a differential, this is an algebraic equation, right? The right hand side here is known to me. So, there are p number of, so this is a p cross 1 vector. Okay, and here also we will have C is a p cross n matrix and x is a n cross 1 vector. So, it is almost like I am solving for px equal to q, linear equation. Of course, for each time instant I have to solve it. Now, I can always ask, why not I just solve this equation and get to the x? Now, the problem with this is, first of all, is it solvable? Yes, it is solvable, because I know that the output equation always follows this rule. Okay, so therefore, I know that this is solvable, but the only problem here is that p is less than n in general. So, if p is less than n, then what will happen? That means this is a matrix, this matrix is a fat matrix, in the sense the number of columns here are more compared to the number of rows, and which means that this the rank of C, let me call this part, let me call this Q. So, the rank of CQ must be equal to rank of C. Even if this is true, we know that the rank of this will be less than n, right, because C has p number of rows and p is less than n, and we know that the rank of a matrix, the rank of C has to be less than or equal to p, and p is less than n, which means that this will be satisfied, and which means that since the rank of CQ equal to rank of C is less than the number of unknowns, we will have infinitely many solutions, and that is the problem, right. If you have infinitely many solutions, what we are basically saying is that there can be different x for which you can get the same y minus du, but we know that means I will have many x's, x1, x2, or let me not write it as x1 and x2, x bar, x hat. So, I can have many different x's that will solve this equation, but among these, which one is the one that actually is the state, we do not know, because the physical the actual plant will be following one of these states. I do not know which one is the actual state. So, I cannot go ahead and solve this equation this way. So, what to do then? Now, here is the trick. So, what we will do is we will find y dot, and y dot is nothing but c x dot plus du. Here u1 means u dot, un means d to the power of n, dt to the power of n ut. So, this can be written in a short form in this way. Okay. So, this is a standard notation in mathematics. So, y dot can be written as c x dot plus du dot, and then x dot is ax plus bu. So, we have cax plus cbu plus du dot. Similarly, if I go for y double dot becomes cx double dot plus du double dot. X double dot can be written as cax dot plus bu dot, again plus du double dot. Again x dot can be replaced by ax plus bu. So, I can keep on going, and this is how, this is the equation I get for y double dot. If I keep on doing this, I will recursively get this equation, and these are the equations that we get. Now, how does this equation help us? If I write all these equations y dot, y double dot up to this term in a matrix form, I will get something like this, and I can find out these expressions at a particular instant, say t e. Okay. So, this is what I get. So, I have measured this, I can measure these expressions, right. I measured these expressions and I found out this matrix equation. Now, notice this matrix equation can again be rewritten in this form, because these parts I can take together, the ones which are the matrices which are acting as coefficients of x of t. So, those can be written in this way, and this expression, the left hand side I am calling it to be yte, this matrix I am calling to be gamma, this is ut. Notice that this is known to us because ABCD is known to us, this is known to us because I can measure the inputs, and this is known to us because I can measure the outputs as well. Okay. And this matrix is also known to us because C and A are known to us. Now, this same expression can also be rewritten in this form. This I am keeping on the right, and then rest of the things I am taking in one side. So, this is the expression that we get. This matrix I am denoting by O of AC. So, this is the equation that you get. Now, notice here this is a known matrix, this is a known vector here, I have to find out x of t. What is the dimension of this matrix? C is a p cross n matrix, CA is another p cross n matrix. So, therefore, the number of rows of this will be p into n multiplied by the number of columns will be n. And now, notice that this OAC now has become a tall matrix, right, because Pn is of course more than n. So, this OAC is a tall matrix now. So, now we have an equation where we have a tall matrix here, we have x of t here, and right side say we have q of t being this. So, now what will when can I say that this equation is uniquely solvable? This equation is uniquely solvable if the rank of this matrix augmented with qt is equal to the rank of this matrix equal to n. So, in other words, if the rank of OAC, if I call this q, equal to rank of OAC equal to n. If this is satisfied, I know that I will get a unique solution, and that is what that will happen only when the rank of this tall matrix is equal to n. If the rank of this tall matrix is equal to n, then equation 1 is uniquely solvable, because you see why is that true? Because rank of OAC q equal to rank of OAC, right, and for this to be having unique solution, this must be equal to n, because n is the number of unknowns here, right, and that means that if the rank of this OAC is of this matrix OAC is n, then the system of equation is uniquely solvable. And a system is said to be AC observable if and only if the rank of this matrix turns out to be n. Okay. and this matrix is called the observability matrix. So, if the observability matrix rank is n, then we say that the system is observable. And what is the meaning of the system is observable? The system is observable means that you will be able to find out the states, estimate the states using the input and the output information for a finite duration of time. Okay. If you know that information, you will be easily able to estimate the states of the system. Okay. And this is why observability is such an important idea, because if a system is observable, it is much easy to find out the states of the system, and you can do that using just the information of input and output. What if a system is not observable? When will a system be not observable? A system will not be observable if the rank of the matrix OAC is less than n, right. In that case, the system will not be observable. Now, if such a case happens, then what will happen? Let us see. So, here we have a system A equal to -1, 0, 0, -2, B is equal to 1, 1 and C is equal to 1, 0 and D is 0. And notice that if we find out the observability matrix C, C A, what do we get? C is 1, 0 and C into A will be nothing but -1, 0. And you can see that the rank of this matrix is 1, which means that this system is not observable. Now, let us take an initial condition of the form 0, 10. Okay. Let us take 0, 10 as an initial condition. Okay. Suppose the system is running with this initial condition 0, 10 and another initial condition as 0, 0, the system is running with another initial condition 0, 0. Now, what happens? Notice here, as I have already told, the initial condition is 0, 0, another initial condition is 0, 10. Now, notice if I run the system with these two different initial condition, what will be the effect of the system at the output? Remember, the input that I am choosing here is U, it is a step input. So, in this example, I have kept input as step input, ABCD matrices are given to you. I know that the system is unobservable, okay, and I have taken two cases. One of the cases where the system is running with 0, 0 initial condition, and the other case is when the system is running with 0, 10 initial condition. Okay. Now, you will see that if I run this simulation, notice that for the case when we have 0, 0 for both these cases, you see the state x2, I am just plotting output and the state x2 here. Okay. You will see that the actual state x2 is evolving in this way. So, the dotted lines here are the case when the initial condition was 0, 10, see. So, it is the x2 is starting from 10 here and then it is decaying, okay, it is going down, and the other case was when the initial condition was 0, 0. So, x2 is 0 here and this is how it is running. Now, this is the state evolution, this is how x2 is behaving. Initially it was at 10, then it goes down in this way in a dotted line way, and the other system where the initial condition was 0, 0, x2 was 0. So, the blue line represents that. What is the effect of these two initial conditions at the output? Look at the output. The output in both the cases are exactly the same. Now, think about it. You had run the system for two different initial conditions. The actual system's trajectories are behaving differently. Of course, it will, because you have started the system from two different initial conditions, right. But now, suppose you are an observer, you want to estimate the states, okay, using output and input information. The input information is step input for both the cases, so it is not changing. And from the simulation, you can see that the output also remains the same for both the initial conditions. So, now think about it, using the output and the input, how will you know for which initial condition the system was running? Okay, because the output and the input are the same even for initial condition 0 0 and for 0 10 as well, and that is the issue. If you have an unobservable system, you will not be able to uniquely find out which initial condition the system started with, and if you do not know uniquely as to from which initial condition the system is starting with, how will you be able to estimate the states? That is the issue. So, if a system is observable, this issue goes out, because I can directly find out the states of the system. Of course, I have not yet explained how to get to the find out the state of the system, because the open loop estimator did not work, but how do we use the output and the input information to get to the states, that I have not yet described, but at least hopefully you have understood that why observability is important. Okay. Let me try to make the system observable now. I will just make a slight change and make the system observable, and this will change the system to an observable system, because I have made this one now. Now, I am making this one. Now, once it becomes 1, so then C is 1 0 and CA is -1 -2. This is a full rank matrix, which means the system is observable. Now, let us look at the output, and now notice that, see, the outputs are the output is this. So, we have two different outputs now. The main idea is that we have two different outputs now, corresponding to the two different initial conditions, right, which was not the case when the system was unobservable. So, distinguishing between the actual initial condition was becoming a problem then. So, observability is a must to get to the states of the system, okay, or to estimate the states of the system from input and output. So, we will need observability, okay, and that is what will be an assumption as we move forward in this lecture now. Okay. Suppose the system is observable, then the question is, how do I find out the states of the system? Okay. Now, of course, you can say, why do not I keep on solving this equation and get it? That becomes difficult, right? Every time instant you have to keep on solving this equation, which will become difficult to do. Okay. Instead of that, is there an automated way of getting the estimated states? Okay. And that is what brings us to what is known as Leuenberger observer. Now, what is a Leuenberger observer? A Leuenberger observer is of this form. So, again, this is another system, like for the open loop estimator, we had created a system x hat dot equal to a x hat plus b u, okay, y hat equal to c x hat plus d u. We had created a copy, right. In this case also we will create another system, okay. However, the differential equations governing the system will be little different. What is that little difference? Notice that this was the equations for the open loop estimator. Now, I have also added the information of the output, okay. I have added this information. So, this is the actual output, this is the actual output of the system, and this is the output that the estimator is giving or observer is giving. What is an observer and or an estimator? An observer in our case is a system, is a dynamical system that takes input and output as input and output of the actual plant as input, and then using those information it tries to estimate the states of the system. Okay, that is an observer. So, in general the definition is a system that will estimate the states for you is an observer. Okay. What are the inputs and outputs to that, what is the input to that system will depend on what type of an observer you are using. For example, when you are using the open loop estimator, you are only the input that is going into the observer is only the U information. Okay. However, when you are using a Leuenberger observer, the differential equation just now that you are seeing, you can see that not only U, the Y and Y will also go as input to the observer. So, the observer is a system that takes U and Y as input, using it, it will try to estimate the states of the system. Okay. So, now if you have this type of a system, then how does it estimate the actual states? So, what is the error dynamics? Error dynamics as in what is the difference between the actual states xt and the estimated states x hat. So, let us call that Et, then E dot will become x dot minus x hat dot, but x dot is Ax plus Bu and x hat dot is this equation. I can go ahead and plug that in. and now here y is nothing but Cx plus du and y hat is nothing but Cx hat plus du. I put that here, these two will cancel out. So, I will be left with these expressions. I am taking C common from here, I am left with this, then A minus LC common will give me xt minus x hat. So, my final expression becomes E dot equal to A minus LC ET. Now, notice that if E dot is equal to A minus LC ET, now here L is something that you can choose, right, because L is in your hands. So, suppose you chose L in such a way that the eigenvalues of A minus LC are subset of C minus. In other words, the eigenvalues of A minus LC are all on the left half plane. Now, if I try to find a solution of this, E of t will come out to be e to the power of A minus LC whole t. Oh, I should not write 2 e's because error is also e and exponential is also e. Let me write it as exp, and then you have E of 0. Now, notice that at limit t tending to infinity, what will happen? At limit t tending to infinity, this will go to 0, since you have chosen L such that the eigenvalues of A minus LC are all on the left half of the complex plane, and this means that xt will be equal to x hat t at t tending to infinity. And that is what we wanted, right? We want that the states should converge to the estimated states should converge to the actual states, because if they converge, then I can use it for state feedback. How will I use it for state feedback? Again, we will talk about that, but this will help you to get to the estimated state. So, if I have to look at a block diagram of actually how does the Leuenberger observer is designed, you can see that this is the system that I have, x dot equal to Ax plus Bu, and this is the actual plant. Okay. Now, in this plant, this was the estimator, right, open loop estimator. Remember, this is how the open loop estimator was designed. The problem with the open loop estimator was that if there are disturbance in the actual plant, in this plant, you will not, the open loop estimator has no way of knowing that. However, now what we will do is we will add a feedback from the output, actual output, and the y hat here, the estimated output, will subtract that out and we will put it back into the system L using L. Okay, and this is this brown part is the part which is your observer, and here if I tap in here, I will get the x hat, and this x hat will converge to x if I choose my L carefully such that the eigenvalues of A minus LC are on the left half of the complex plane. Okay. So, let us have a look at a simulation here and see. So, here you can see that we have a system, we have this system, okay, and in this system, so you can see A, B, C and D. If you check, you go ahead and check what is C and CA, okay, then you will see that this is an observable system. Okay. Now, you see this is the actual initial state, okay, this is the plant's initial state, this is the observer state, as again the observer does not know what is the actual state. So, it is an observer's wrong guess. Okay. Let us say that I have chosen L equal to 6. Okay. I mean, how am I choosing that? All that we will discuss, but for now let us assume that this is the L matrix. Then I do two simulations. The first one is the open loop estimator. This is the estimator that we had talked about at the beginning, which had problems because it did not have feedback, and the second one is the estimator, and the third one here is the Leuenberger observer that we have designed. See, I have implemented the Leuenberger observer here, and this part is the true plant, the actual plant with a disturbance. Remember, in the open loop case, this disturbance was creating a problem, right? Let me just put it 0 for the time being. Let me make it 0. So, for the time being, let me make it 0 and let me run the system, and you can see that when there is no disturbance in the actual plant, you can see these are 3 plots. The red line is the open loop estimator, the blue line here is the closed loop estimator or the Leuenberger observer, and the black line here is the actual state, and all of them converges, which we are anyways expecting, right, because now there is no disturbance. But what happens if I put disturbance? Let me put disturbance here. Now, when we put disturbance, remember the open loop estimator was not able to follow. You can see this, right? So, you see the dotted line, the open loop estimator is not able to follow the actual states, but the closed loop observer or the Leuenberger observer is able to follow the states to some extent at least, right. If I run this for more time, the gap between this blue line and the black line will be decreasing further and further. Okay. You can keep on changing the value of L, and you will have different rates at which the estimated states will converge to the actual states. You can check, just to check whether this is actually an observable system. You see, you can easily check that if you find out rank of C into A. See, rank of this matrix is 2, which means it is an observable system. There is another way of finding out the rank. This is an observability matrix. So, OBSV will give you the observability matrix. This is a function, inbuilt function in MATLAB. OVSB AC will also give you the observability matrix. You can look at that. So this is the observability matrix. Okay. What is the eigenvalue of A minus LC? Okay. A minus LC. Remember, A minus LC is the matrix that governs the error dynamics. E dot equal to A minus LC into ET. So, the eigenvalues of that are minus 5 and minus 2.5. If I change the L to say 16, let us see how will it change. Okay. If L has been changed, now you see the estimated states are much closer to the actual states. It is going faster towards the actual states, because now you can check that the eigenvalues of A minus LC is also further away from the imaginary axis. So, what is basically happening here is that, see, in the first case, what is the dynamics? The dynamics is this, right? The error dynamics is this. So, I know that this will e to the power of our exponential of A minus LC whole of t, E of 0 is equal to the actual error, the rate at which the error will go down to 0 will be given by the eigenvalues of this part, A minus LC, right. So, further the eigenvalues of this matrix to the left from the imaginary axis, the quicker the error will go to 0, and that is what was demonstrated in the simulation. So, till now what did we see then? We have now come up with this idea that if we use a Leuenberger observer, okay, in that case, using the information of the actual output and the input that is given to the actual plant, we can automatically estimate the states of the system. Okay, and the rate at which these estimated states will converge with the actual states depends upon the eigenvalues of A minus LC, right. So, in A minus LC, L is the parameter that is in our hand. We will be able to change L. If I change L in such a way that the eigenvalues are where I desire, then I will be able to converge the estimated states to the actual states quicker. In the next lecture, we will actually look at this, that how do we find out that L matrix, okay, and that will bring us to the idea of duality, okay, and we will do that in the next lecture. Thank you.